Namaste and welcome to the lecture series on the subject Basic Thermodynamics, Module 2, in that part 2, First Law of Thermodynamics, lecture number 12. So myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Mangalur. So in this lecture and in the next two lecture also, I am going to solve the numericals on the first law of thermodynamics. So let us take this numerical first. So in a cyclic process, heat interactions are plus 14.7 kilojoules, minus 25.2 kilojoules, minus 3.56 kilojoules, and plus 31.5 kilojoule. To stop, what is the net work for this cyclic process? So you are given the 4 heat interactions and you are supposed to find out the net work. And as already you studied, for a cyclic process, the cyclic integral of heat transfer is equal to cyclic integral of work transfer. Okay, so you are given the heat interactions, so you can calculate the cyclic integral of heat transfer del Q. So that is nothing but Q1 plus Q2 plus Q3 plus Q4, which will be equal to the net work. So your net work directly you can get by adding the 4 heat interaction, as the cyclic integral of heat transfer is equal to cyclic integral of work transfer. Okay. Okay, now let us solve the next numerical. Consider a cyclic process in a closed system which includes 3 heat interactions, namely Q1, Q2, Q3. So Q1 is equal to 20 kilojoules, Q2 is equal to minus 6 kilojoules, and Q3 is equal to minus 4 kilojoules, and 2 work interactions for which W1 is equal to 4500 Newton meter. Compute the magnitude of the second work interaction, W2 in Newton meter. Okay, it's very interesting here. You are given 3 heat interactions here, so they are named as Q1, Q2 and Q3, and two work interactions, W1 and W2, and you have to find out the W2. So once again you have to use the first law equation for the cyclic process, that is cyclic integral of dq is equal to cyclic integral of dw. Okay. So for a closed system undergoing cyclic process, you have cyclic integral of del q is equal to cyclic integral of delta w. So if you add the 3 heat interactions, now here Newton meter is nothing but joule. So here it is 4500 joule, but here all the heat terms are in kilojoules. So what you have to do is you have to make it joules. That is what 20,000, minus 6,000 and minus 4,000. So that is nothing but the cyclic integral of del q. On the other side you have 4500 plus W2. So it's very simple. So you will get W2 as 5500 Newton meter. So positive sign. Okay. Next, number 3. When the state of a system changes from state 1 to state 3 along the path 1, 2, 3 as shown in figure, 80 kilojoules of heat flows into the system and the system does 30 kilojoule of work. First one A, how much heat flows into the system along the path 1, 4, 3 if work done on the system is 10 kilojoules. B, when the state of the system is returned from state 3 to state 1 along the curved path, the work done on the system is 20 kilojoule. Does the system absorb or liberate heat? Find its magnitude. And number C, if U1 is equal to 0 and U4 is equal to 40 kilojoules, find the heat absorbed in the process 1, 4 and 4, 3 respectively. So here you are given a PV diagram wherein the system changes its state from state 1 to state 3 along 3 different paths. So one is 1, 2, 3, other one is 1, 4, 3, next is the curved path 1A3. Now here you see this is a PV diagram. So 1 to 2 is a constant volume process. Similarly 4 to 3, so your arrow mark has to be in this direction. So 4 to 3 also has is also a constant volume process. Okay, and 2 to 3 and 1 to 4, so they are the constant pressure process, and there is a curve, some other process through which the system moves from state 1 to state 2, 3, so that is 1A3. Now here, so yes, he says that when the state changes from state 1 to 3 along the path 1 to 3, so you have to consider 1 to 3, then the 80 kilojoules of heat flows into the system, that is Q3 minus Q1, sorry, not Q3 minus 1, Q1 to 3. Okay, Q1 to 3 is 80 kilojoules, and the system does 30 kilojoules of work, that is W1 to 3 is 30. See, when for a path, if heat flow is given, so you have to take it for the path, because it is not a point function, so it is Q1 to 3 and work is W1 to 3. So these two parameters are given for this problem, and the remaining you have to solve. So let me consider one by one instead of confusing you in the next slide. So let us take the first part A, so that is along the path 1 to 3. So 1 to 2, sorry, 1 to 2, okay, then 2 to 3, so this is 1 to 3, this path. So process is moving from state 1 to state 3 along the path or along the point path 1 to 3, okay. So from the first law of thermodynamics, you know that Q1 to 3 is equal to, okay, you can put bracket here, U3 minus U1, that is delta U, okay, and plus W1 to 3. So here Q1 to 3 is given and W1 to 3 is given, so you can calculate U3 minus U1, right. So U3 minus U1 you will get as 50 kilojoules, because you are given Q1 to 3 and W1 to 3 as 80 and 30 respectively. So U3 minus U1, that means internal change, energy change during the process 1 to 3 or along the path 1 to 3 is 50 kilojoules. Now let us consider the path 1, 4, 3. So you have to look into this path 1, 4, 3. So here for the writing the first law expression for this path, so you can write Q143 is equal to U3 minus U1. You see here, like previous expression here, the internal energy change is always a point function. So that you would write the difference of the final value minus the initial value. So it doesn't change for the path 1, 2, 3 as well as 1, 4, 3. So this term U3 minus U1 here for path 1, 2, 3 and here for path 1, 4, 3. So this remains same. Okay, and the remaining quantity heat is Q143 and W is W143. Now we will see what is given here. So W143 is given. You can check the previous problem statement. So W143 is 10 kilojoules and U3 minus U1 we calculated in the previous part above. So that is 50. So Q143 you will get it as 60 kilojoules. So here the problem is very simple. Only thing is you should know how to apply the first law equation to this process or to these paths. Okay. Okay, now let us take the second part B, that is for the path 3A1. So once again you have to go back and you have to read that question. Suppose if you already noted down, then it is fine. So here, so you can apply the first law equation Q3A1. So starting or moving from 3 to 1, so it is 3A1. So here it becomes delta U becomes final minus initial, means U1 minus U3. That's very important. And W3A1. So here U1 minus U3. So now you calculated in the previous slide. What you calculated is U3 minus U1. So U3 minus U1 is 50. So U1 minus U3 becomes minus 50. And work is given as minus 20. So here the net total heat transfer is equal to minus 70 kilojoules. Okay, so negative sign indicates that heat is liberated from the system or heat is removed from the system. So next C, so that is along the path 1, 4. So 1, 4 means you can see, so this from here to here. So only for this process you have to apply the first law of thermodynamics, that is Q1 to 4 is equal to U4 minus U1 plus W14. So here Q4, if you look into the statement, it is given as 40 and U1 is 0. So U4 is 40 and U1 is 0 and W1 to 4. Now to calculate W1 to 4 you have to use this expression W143, that means from here to here whatever you calculated earlier, which is nothing but a summation of W1 to 4 plus W4 to 3. As I told you earlier, this 4 to 3 is vertical, it is perpendicular to volume line axis, so it is a constant volume process, so work done during that is 0. Then W143 becomes equal to W14, okay, which is nothing but 10. W14 becomes 10. Now if you substitute here that 10, so you will get Q14 is equal to 50 kilojoules. Now positive sign indicates that heat is absorbed by the system. Now coming to path 4-3, so Q43 is equal to U3 minus U4 plus W43. So just as I discussed now, so here 4 to 3 is a constant volume process, you can see here. So this term is 0. And here U3 minus U4, so you don't have any data to calculate that U3 or U4. So what you can do is, so U3 minus U4, so you can write as U3 minus U1 minus U4 minus U1. So here this U1 gets cancelled with this U1. Ultimately it is U3 minus U4 itself. But you are rewriting that as U3 minus U1 minus of U4 minus U1. So U3 minus U1 you calculated in the previous slide as 50 and U4 minus U1 is here. Okay, so that is 40 minus 0, so that is 40. And W43 is a constant volume process 0, so you will get answer as 10 kilojoules. Okay, now let us move on to the next problem. A domestic refrigerator is loaded with food and the door closed. During a certain period of the machine consumes 1 kilowatt hour of energy. So total energy consumption by the refrigerator is 1 kilowatt hour and the internal energy of the system drops by 5000 kilojoules. So internal energy drops means it reduces by 5000 kilojoules. So find the net heat transfer for the system. So it's a very simple problem. So W122, that is, you know, it is a refrigerator. So refrigerator is a work absorbing device. So it is consuming work. So means work should be taken as the negative because work is done on the system. So it should be taken minus 1 kilowatt hour. So this kilowatt, so which is nothing but kilojoules per second. So you have to multiply by hour. Hour is 3600 seconds. So that second gets cancelled. I'll show you. Kilowatt is nothing but kilojoules per second. Okay, and into hour is nothing but 3600 seconds. So here the seconds term here gets cancelled with this here, so it becomes 3600 kilojoules. So that's what 1 kilowatt hour is 3600 kilojoules. Is minus sign is there, it is minus 3600 kilojoules. And internal energy drops. So final minus initial, U2 minus U1 is minus 5000 kilojoules. Very important. So you have to be extremely careful with the sign convention when you solve the problems on this, especially the heat transfer, work transfer and the changes in the other energy quantities. So here internal energy is decreasing, so it is minus 5000 kilojoules. So from the first law, okay, first law you have Q122 is equal to U2 minus U1 plus W122. So Q122 you have to calculate. U2 minus U1 is minus 5000 and that is minus 3600 W122. So just substitute. So you will get it as minus 8600 kilojoules or minus 8.6 megajoules. So this is the net heat transfer into the heat transfer for the system. That means so much of heat is removed from the system because it is minus. Okay, so the negative sign indicating the heat removal. Okay, now let us go to the next problem. For the following process in a closed system, find the missing data. So it's very interesting. and very simple too. You are given 4 processes A, B, C, D. For each of these processes, for few of the values are given. So the values are Q, W. So let me show you here. So you have Q here, W, then initial internal energy, final internal energy, and delta U, which is nothing but U2 minus U1. This delta U is nothing but final minus initial U2 minus U1. So there are few dashes in this table. So which you have to fill. Once again you have to use the first law equation. So let us start from the process A and start filling the table. Okay. Now this is the basic equation which you have to use. Q is equal to delta U plus W, or U2 minus U1 plus W1 to 2. So here also you can write, if you want, you can write Q 1 to 2 for your convenience. Q1 to 2 is equal to U2 minus U1 plus W1 to 2. So this is the basic equation which you have to apply for all the 4 processes. Okay. So here for the process A, okay, so delta U is U2 minus U1. So delta U is given here and U1 is given. So only U2 is unknown. So by using the very basic internal energy expression, delta U is equal to U2 minus U1. So you can calculate U2, which you get it as 5 kilojoules. So this value is 5 now. Because U2 minus U1, minus of minus plus 10 plus 5 is 15. So that is how you can check your answer. Now once you find out delta U, easily you can find out Q. Because Q1 to 2 is equal to U2 minus U1 plus W1 to 2. So W1 to 2 is 20. So you will substitute that. So you will get Q as 35 kilojoules. 15 plus 20. So what is 15? Delta U. Okay. Or directly you can write as delta U plus W also. No issues. Q is equal to delta U plus W also. You can consider. Or in place of delta U, you can consider U2 minus U1 also. Now let us consider the process B. So now here in this table, I already wrote the value of U2 and Q for the process A. Now here two unknowns are there, U1 and delta U. So now Q and W are known. So it is very easy because you can directly find out delta U. Once you know Q and W, so use this expression Q is equal to U2 minus U1 plus W. So once again here I repeat, here you can use the suffix 1 to 2, here also you can use the suffix 1 to 2, or without suffix also you can solve. So Q and W are known, so okay, or directly you can substitute for even U2 and U1 if it is given. So here U2 is given, substitute it as minus 6. So U1 is only unknown, so directly you can get U1 as minus 27 kilojoules. So U1 as minus 27 kilojoules. Later you can calculate delta U, or instead Q and W you can use that and you can find out delta U first, then you can find out U1. So one and the same. Then delta U is equal to U2 minus U1 is equal to 21 kilojoules. Okay. Now let us move on to the next process, that is here you can say U2 and delta U are not known. So once again same relation, because when Q and W is known, so you can find out directly U2 or you can find out delta U also. Same formula. So minus 7 is equal to U2 minus 20 plus 10. So you will get U2 as 3 kilojoules and delta U as minus 17 kilojoules. This is how easy it is. Very easily you can calculate. Only thing is you have to understand the basics. Okay. Next process D. So process D. Now you can see here Q is not given. Okay, here, and W is given. So if you want to calculate Q, you should know the value of delta U. Okay, delta U is given. So with these three, you can find out what is Q. Now to find out U1, you have to use the formula delta U is equal to U2 minus U1. So first we find out delta, you can find out U1 using the formula delta U is equal to U2 minus U1. So by substituting, you will get U1 as 28 kilojoules. Now use the first law equation and you will get Q as minus 27 kilojoules. So all of you can try to solve this without looking into the slides, and you can check your answer in the next slide. So here I filled the entire table with the answer, so you can verify your answer. So try to solve this problem without looking into the solution, because you need to understand the basics first. So with this I conclude the lecture number 12. So we'll solve few more numericals in the next two lectures. Thank you.